Okay, so the recording started, so we can start.
Okay. Welcome, everyone. Thanks for coming to the RL Theory seminar. I guess this is the first in a series of talks we'll do for the, the spring quarter or whatever. The first talk for the series is by Max Simchowitz. It's my great pleasure to introduce him. I've known Max for like almost 10 years, and in that time, he's had quite a dynamic research career spanning topics in learning theory, core reinforcement learning theory, control, fairness, all sorts of things. He's very strong, very capable. He did his PhD at Berkeley. He spent some time at MIT as a postdoc, and now he just started as an assistant professor at Carnegie Mellon. And he's going to tell us about imitation learning in continuous spaces, and I guess some pitfalls there. Just for admin stuff, I think it's okay to do questions during the talk. If you don't want to do that, you can raise your hand. I'll monitor. Or you can just type in the chat, and I'll interrupt, or you can also interrupt, I guess, as appropriate. With that, Max, take it away.
Hi, Akshay. Thanks for the introduction, and thanks everyone who took the time to make it to the seminar. So maybe a little bit about my journey before I begin is I did sort of a PhD in kind of more traditional learning theory, but I had the fortune to spend a few years in a robot lab in MIT. And I think it's really changed how I think about some of the problems and how it's caused me to reflect on how some of the assumptions that we make in RL and RL theory might need to be adjusted if we start thinking about the continuous action world. And so I'm going to present some work that kind of tries to make some of these points a little bit more clear. So maybe it's kind of every talk in machine learning, it feels like one is obligated to begin with language models. And so, one way to view language models is just some form of expert learning or learning from an expert, right? So we can view natural human language as an admittedly imperfect expert. And here, what we're trying to do is condition on observations, in this case, sequences of previous tokens. And the action that we're trying to predict is simply what is the next token in the sentence that we want, right? It's a natural model of what's going on in languages. And we can think about a similar paradigm occurring in large robotics models as well, right? So right now, people are actively collecting data to train large foundation models for robots. And again, one way they're doing this is they're collecting large amounts of human demonstrations. So this is from collaborators at Toyota Research Institute. They're collecting human demonstrations of interaction with the robot. And the aim is just to train the robot to predict the next action the demonstrator would give. Again, using observations like pixels or tactile sensing as a form of a conditioning variable. So similar paradigm. So I think a couple questions we can ask is, looking at the language model regime, will scaling solve the problems of robotic foundation models? What is the importance of on-policy data we need for robot models, or can all this done purely from offline demonstration? And maybe how should we design the forms of the robot policies that we need in order to scale up these systems, right? These are some questions that we should keep at the back of our heads. And so when I think about these problems, I see a lot of formal similarities, right? In language, my goal is to predict tokens, whereas in robotics, my goal is to predict actions. But maybe in language, they're discrete, and in robotics, they're continuous. And I guess a major question is, are these things meaningfully different, or are they just somewhat superficial in their differences? Right. So is there a fundamental difference here? So maybe we can set up, right? So if you open up an RL book or an RL textbook, maybe RL theory paper, what you'll see is the following notation. You'll see states denoted with the letter S, actions denoted with the letter A, and you'll denote dynamics as being drawn from some transition probability distribution, transition kernel denoted as in the slide, and maybe a policy is just some distribution over actions, again, denoted typically in this way. And in robotics or in control, we use somewhat different notation, right? So here we use X for states and actions are U, control inputs. Our dynamics, rather than thinking of them as coming from some arbitrary conditional distribution, we envision having some nominal dynamics function, typically denoted F, and maybe there's some noise that affects the dynamic process. And then finally, again, we can draw control inputs from some policy distribution. So maybe the semantics here are somewhat different, right? So in language models, our states, oftentimes we think about this as being, say, sequences of tokens, maybe words, right? And our next action is the next word. Whereas sort of in robotics, we think more of X as being either observations or system state, U as being a robot action, but notably these are continuous valued, right? So a lot of formal similarities, but maybe slightly different semantics. So in both problems, we want to say imitate an expert. So what's a reasonable way to talk about imitation? What we can do is we can look at some notion of excess cost. So we can fix some notion of cost, we'll call it C. And our notion of error will be looking at the cost under the imitator policy, which we call pi hat. This is what we learn with data. And we compare this to the cost under the expert, right? And so our notion of excess cost, you could call this regret, basically determines how well we're doing imitation. Right? And typically in this problem, we're going to focus on problems over a certain horizon, certain number of steps, which we'll denote by H. And horizon will become kind of a key factor in our discussion. Right, so there are a lot of ways that you can kind of try to minimize this imitation error. So one possible way to do this, not the only way, is through what's called behavior cloning. So behavior cloning, what you do is you specify some loss function, which, and here I'm going to be using the control notation, X and U, which basically measures how well your policy is doing relative to pairs of states and actions in your expert, from the expert data. Right, and there are many loss functions that you can minimize, and basically you just train pi hat to fit the expert data by minimizing this loss, at least to the best of your optimizer's ability. So you might do this by minimizing a square loss if you'd like. This typically works if pi star is deterministic. You might do this by minimizing an indicator loss. This probably makes more sense if pi is discrete. You can use the log loss. So Dylan's got some awesome work about why that might be beneficial to work with. Also works if pi has some continuous density. Or you could even use things based on score matching, which have become quite popular in sort of diffusion policy, parameterized policies, right? That also works quite well. And it's very popular in robotics. But sort of kind of importantly is even if you're not going to do sort of explicit minimization of the Litz loss, I think it is very natural to compare to the sort of best you could hope for under minimizing this loss as a benchmark of how difficult the problem is, at least statistically. Right, so what we'll do in today's talk is we'll compare our notion of imitation error to basically what we would expect to get if we were just looking at how big the loss was, but crucially under the distribution of expert data. So we look at the distribution of expert data, this is this expectation, and we measure how large the loss is. And roughly speaking, we'll try to understand this as a proxy for how easy the problem is statistically without dealing with issues related to the dynamics of the system, just how easy it is to fit the expert data, even if we consider algorithms that don't necessarily do this minimization algorithmically. Okay. So why is behavior cloning hard? Well, it relates to this phenomena called compounding error, right? So our notion of expert imitation accuracy, right? How close we'd be on fitting a supervised learning objective on the expert data. You can really think about this as basically taking samples from an expert trajectory and making sure that you're able to make predictions which at each individual time step are close to what the expert would do, right? So this is what it would look like to have a small notion of our expert. But unfortunately, what we really care about is not our expert. What we care about is sort of the deployment behavior of the learn policy and what cost that attains. So expectation under the learn policy pi hat. And when you actually deploy the learn policy, what you start to see is that the errors that it makes can possibly add up. In fact, errors can accumulate over time steps, and they can in fact accumulate more and more largely as the horizon grows. Moreover, after the error has accumulated, you can also run into the fact that you might be out of the distribution of your expert data. So you might sort of end up somewhere over here where you don't have a lot of supervision and you don't quite know what action to take next. Right? So this is an issue that you can run into. So what do we know? Well, it's very popular, actually, even kind of going back to kind of early work on imitation, to compare sort of imitation and imitation in this sense to imitation under this expert sense. Let me cancel the self-work update. And so, for example, if we are in a setting where we can minimize the 0-1 loss, and we consider costs that are bounded in 0-1, then roughly speaking, we can bound our notion of imitation under a certain cost, that should have an R sub C, by roughly H times the expert error, right? H, a horizon factor times the error of the imitation in the 0-1 loss. And there's some really wonderful improvements that can be made if you are able to consider other loss functions under certain kind of assumptions on your function class. And so what this basically tells you is, compounding error is maybe linearish in the horizon, depending on how you parameterize things. Maybe it's a little bit better than that. But it would seem like compounding error, the horizon dependence of your problem is not such a significant obstacle. So actually, I'm going to say that maybe this perspective is not the one that we should take in the continuous world, and I'll justify why. Right, so many forms of imitation, including ones that have been popularized recently in LLMs like log loss, really they sort of imply guarantees that would imply imitation in the 0-1 loss. So for example, with Pinsker's inequality, you can sort of control total variation distance by log loss. If that doesn't make sense to you, don't worry about it. If you're an expert, you understand what I'm saying. So essentially, what basically needs to happen is you need to be able to imitate in 0-1 for any of these kind of interesting linear or sublinear guarantees to make sense. Okay. So consider just a scalar prediction problem, right? So I just sample some context vector uniformly from 0, 1, and I try to learn some function of that scalar. And suppose I just try to minimize the 0, 1 loss for just scalar prediction, right? So here, these things might be continuous valued. Is this possible? For those of you that know some basic statistical learning theory, you'll say, of course, it shouldn't be possible in general. And in fact, you can make this formal, right? So you can show that there are classes of sort of just single step functions where given n examples, sort of you can't get anything better in the 0, 1 loss than not in trivial error. So the worst possible error in the 0, 1 loss is an expected error of 1. But at the same time, you can actually learn, let's say in the L2 loss, with vanishingly small error. So you can make the error go down as a function of number of samples n as fast as you like, and yet you still cannot learn the 0, 1 loss, right? And this is kind of easy to see. One way to construct this example is to build a Fourier series and show that estimating in the 0, 1 loss allows you to perfectly recover every Fourier coefficient, but sort of L2 estimation just needs you to sort of approximately recover the first few, and this is feasible from some amount of data. And you can actually make the rate of estimation improve as you make the decay of the coefficients go faster.
Wait, Max, I'm a bit confused. So here, the class pi is not known to the learner.
Oh, it is known to the learner. I'll give you a class pi known to the learner. So there exists a class pi which is known to, which I can tell the learner, where I can't estimate in the 0, 1 loss, but I can estimate in the L2 loss, and I can adjust that class for whatever I'd like to make estimation at L2 loss as fast as possible.
I see, but that class is not a singleton. That's a large class.
It's a large class, yes.
Okay, good. Okay.
Yeah, it's not a singleton. Sorry, it should be set of pi and pi. That's a good clarification. Thank you.
Awesome.
Yeah,
thanks.
Cool. So basically, the key implication is that these assumptions under which we get this linearish compounding error, they're not really applicable in continuous state space, right? So far, all I've done is convince you that like thinking about 0, 1 loss might be the wrong thing for continuous state spaces. I haven't yet shown you that compounding error necessarily might be a problem. So let me kind of make this a little bit more precise. So I really like proving lower bounds. And one thing I think is an important part of the art of lower bounds is to prove them in settings that you might otherwise think are nice or benign. So the lower bound I'm going to prove to you today is going to be in what we might think of as one of the nicest control systems that you could think about. And let me try to convince you that this is a nice system. So the first thing that's going to be nice is that the expert and the dynamics are deterministic. In particular, there's been a lot of work in robot learning around learning multimodal policies that are complex distributions. Instead, we're just going to think about learning deterministic experts. The second thing we're going to assume is that the dynamics in the expert are C infinity. They have infinitely many derivatives, and their first and second derivatives are bounded, right? So they're going to be Lipschitz and smooth, right? Also a nice property. So there's nothing like stiffness or discontinuity of the dynamics that's going to get in your way. And the final property, which I'm going to spend some time explaining in a couple later slides, is that the dynamics are exponentially incrementally input to state stable. This is a mouthful, but roughly what this means is that the dynamics are somewhat insensitive to perturbations. So it's not the case that if you make a small error, suddenly you end up in a totally different place. Roughly speaking, small errors shouldn't make a big difference to the dynamics, even on longer horizons. And we'll talk a little bit more about this assumption. So we're going to get back to that assumption later. I'm going to explain it in greater detail. Last thing what I'm going to say is that our lower bound does not apply unconditionally. It applies to basically any algorithm, be that online, be that behavior cloning, offline reinforcement, learning, inverse RL style approaches, but it in particular constrains the class of policies we're allowed to use. So we're going to prove a lower bound against what we call simple imitator policies. And then I'll explain to you at the end of the talk how things generalize beyond that. So I'm going to define a simple imitator policy as a policy that has two components. It has a deterministic component, which, like the expert, I'll assume is Lipschitz and smooth. And it also has a stochastic component, which is going to be assumed to be independent of X. So we can see that simple policies are a strict and pretty strong generalization of the kind of class of policies that the expert can be. But nevertheless, they don't capture every policy. So for example, a common policy parameterization in sort of like simple robot learning tasks might be a mean policy where you parameterize the Gaussian mean, but you don't learn the Gaussian variance. You treat that as a fixed parameter, or you treat it as a fixed parameter across all states. And this would constitute being a simple policy, right? Not a non-state varying variance in the Gaussian. And again, for non-simple policies, actually, that's where the story gets very interesting. That will be the end of the talk. So let me give you an informal statement. You can pick your favorite number, K, favorite natural number. And what I'll show you is a family of nice imitation learning problems. So a class of pairs of dynamics and policies, which lies in 3 dimensions, only 3 dimensions, such that given n sample trajectories, there is an algorithm which can imitate in, let's say, the L1 expert loss, or you can do L2 expert loss. This also works, but you have to tweak things just a little bit, but can estimate, basically as fast as you'd like. So it can estimate at a rate of 1 over n to the k, right? You can make k as big as you want. And so notice that unlike the 0-1 loss, we actually now have a notion of expert loss that can be minimized and can be minimized provably under our construction, right? So what this says is it says that supervised learning on the distribution of the action of the demonstrator is easy. It's easy statistically. But if you try to learn a simple policy, there is a one Lipschitz and a bounded cost function. So a cost function that's not too non-smooth, it's not unbounded, such that if you try to imitate and return only simple policies, your error is at least a constant times either like about 1, either it's a constant error, or it's 2 to the horizon times your imitation learning error, right? So again, you can't, because costs are bounded, of course, your error can be at most a constant, but in the regime where the imitation learning is small, it can be at most a 2 to the horizon factor larger, right? So this is a considerably larger effect of compounding error than we saw in the discrete setting, which was linear in horizon, 2 to the h. And again, recall that this is measuring the excess cost of the imitator relative to the expert, right? So this is kind of like the kind of big result of our findings. So a couple of remarks, right? So I think the most obvious one is now the deployment error, this R sub cost, is exponentially larger than the expert distribution error. The second remark I think that's kind of powerful is that our result depends on the structure of the imitator policy itself, and we'll see how this arises from the proof. But it doesn't depend on the learning algorithm. So behavior cloning, offline reinforcement learning, inverse RL, the version that doesn't use on-policy data, just tries to learn a reward and optimize it offline. None of these approaches are going to work, right? It's truly a limitation of the policy class. And finally, what we'll show is how to break our lower bound with sufficiently improper policies. And, improperness has always been like a really kind of powerful theme in sort of statistical learning, but we're actually going to see that some of the ways of being improper that break our lower bound kind of give evidence to some of the successes in recent robot learning policies. And that'll be the end of the talk, showing how kind of recent advances in robot learning actually break our lower bound in kind of interesting ways. So I think the first thing that I'd like to do before going into the kind of sketch of the proof is to explain to you what I meant by a nice control system in a little bit more detail. So recall we assume that our dynamics and expert are deterministic, and recall that we assume that these deterministic functions are both Lipschitz and smooth, have bounded first and second derivatives. But the real kind of weird assumption that maybe the audience might not be very familiar with is this notion of stability, of exponentially incremental input to state stability. And it's not really clear at this point what this means. So let me kind of first begin by pointing out what is instability in control systems. Right, so a control system, we can think of a scalar control system. It's actually linear, where the dynamics as a function of x and u are equal to twice the state x plus the input u. Right, this is a scalar control system. And so let's consider two trajectories. Both trajectories start at the initial state x equals 0. In the first trajectory, your inputs are always selected to be 0. But in the second trajectory, your inputs are always selected to be some number delta, right? Some small parameter delta. So what happens when you plot these two trajectories on a line? Well, your first trajectory will always remain at 0 because you have a linear system that starts at 0 and you're always putting 0 in. But if you start feeding in delta into the system, what you can show is, in fact, basically the magnitude of the state will grow by at least twice to the horizon, because you get a factor of 2 here, times delta. Right? So we call this an unstable system because the small perturbation delta gets magnified exponentially by the dynamics of the system. Right? This is a kind of one of the simplest examples of an unstable system. Right? So we can think of systems that have high sensitivity to perturbations in the inputs as unstable, and that's kind of their more kind of formal definitions of this. So informally, you can show that if you have an unstable system, basically there exist learning problems which are deterministic, that are smooth but are unstable. And every learning algorithm, no matter what you do, will basically have exponential compounding error for all sufficiently large, for all horizons that are smaller than exponential in the dimension, right? So what this says again is that the policy is easy to learn on the distribution, but when you try to deploy it, you have exponential compounding error. And this horizon less than e to the dimension comes from the fact that you can always cover this space. So it's kind of interesting there. But basically, this says that there's nothing that you can do in an unstable system that will help you. But in some sense, this is kind of like uninteresting, right? So like, again, back to the art of proving lower bounds, it's not fun to prove a lower bound in a difficult situation because we expect things to be difficult. If we expect our system to be very sensitive to perturbations, obviously this is going to make compounding error worse. And moreover, kind of from a practical perspective, instability shows up a lot in classical control regimes like aeronautics, but we don't really believe that robot learning is an unstable problem. We believe that, much of robot learning is sort of very plastic. The robot has a lot of compliance in its joints. And so instability, while nice for proving counterexamples, is maybe the wrong paradigm to be thinking about. So let's actually turn back to nice systems that are stable. And I'm going to introduce a definition of stability that we'll explain in kind of greater detail. So we say this system is exponentially stable, incremental input to state stable. It's a mouthful. I'm just going to call it exponential stability for now. If you take two initial states and you take two sequence of control inputs, and they have the following property, that the difference between the state at some time h plus 1 decays exponentially with some parameter rho between 0 and 1 times the initial norm or distance between the two states, plus some basic kind of like weighted geometric sum decaying as rho to the kind of distance of that time step from the current time step times the distance between the two inputs, right? So this kind of says that basically you have exponentially fast attenuation of the initial condition and distances in the inputs towards the current differences in the state, right? You can think of this as a forgetting condition. It basically says that your system just forgets things exponentially quickly, modulated by this parameter rho. So I'll give you an example of this. If you had a system of this form, you started the same states, but now you perturb the inputs by a factor of delta. What you can show is that basically the differences in the states will remain order delta apart for all times t. Like unlike the unstable system where things are growing with t, here all the states are going to be close to one another. So this is our notion of incremental stability. So let me kind of explain how this might look geographically, or look up sort of pictorially. So you can imagine a system, what we call open loop. So this says I put in inputs to the system and I see what comes out. And these inputs are not viewed as functions of the state. So open loop incremental stability says the following. It says if I imagine some malicious adversary that's going to take these inputs and corrupt them by some amount delta, then the resulting kind of response of the system to these corruptions is going to be roughly pretty close to the original dynamics. Right? It just tells you that these two things are going to track each other pretty well, as long as this adversary is constrained to only kind of making very small perturbations. So that's incremental stability. Perturbations of input lead to bounded states. Actually, not very small, just sort of the perturbations here are proportional to the perturbations here. You can also talk about this in closed loop. So in control and closed loop, what we mean is that basically the inputs are being fed back into the system. So we'll say that the expert policy combined with the dynamics is closed loop EISS. If when we think about feeding the expert back into the policy, right? So into the dynamics, so we take f of x, your inputs are the expert policy evaluated at x plus some perturbation. These also have the stability property. So pictorially, it looks like this, right? So you take some inputs to the control system, you get out some states, but now your expert policy depends on the states that arise, right? So it's what we call in control closing the loop, feeding the states back into the policy. And what kind of expert closed loop EISS means is that the kind of adversary is allowed to slightly perturb these inputs that the expert would have taken, put them back into the system, see the new state. But crucially, the expert policy is evaluated on the new states that the kind of adversary sees. So we call this kind of incremental stability in the sense that the adversary is only perturbing over the expert, but on its own trajectory, right? And this is the picture that we have here. So these are kind of two very kind of nice, desirable behaviors that one might have in the control system. And again, this ensures that these things are close. So ultimately, what we've done is we've defined what we mean by a nice control system. We're going to assume that both the open loop dynamics, right, just the dynamics itself, but also the closed loop dynamics, what the expert would do, are both sort of exponentially insensitive to perturbations. These perturbations become forgotten exponentially quickly. Right? So this is kind of the most that you can hope for from both an expert and from a dynamics function in terms of being kind of regular and well-behaved. Cool. So again, right, what does our theorem tell us? Our theorem says even under this exponential incremental stability condition, we still have exponential compounding error. And this should surprise you, right? Because on the one hand, I've told you I have a property that makes my systems exponentially forget errors really quickly. And on the other hand, I've told you that I have a setting where I can learn how to do the right thing, but yet this perturbations I make by like not estimating perfectly compound exponentially largely through the system, right? So these two properties seem to be at odds, right? That the system forgets perturbations exponentially quickly, but that learning is sort of exponentially sensitive to these perturbations. So I want to kind of explain how it's possible for these two things to kind of coexist. And sort of to do this, right? To do this, I'm going to actually dive into a very simple example from linear control. Explain what can go on.
Okay. Hey, Max, I have a question.
Yeah.
So somehow in my head, I'm trying to figure out why this is true also. And I'm in my head, I feel like actually having noise in the dynamic could help you, because like once you make a mistake, you're like completely OOD.
Exactly.
So having mistakes are like completely uncontrolled in some sense. But maybe if there's noise, you're actually not really OOD. You're just like shifted in distribution.
Exactly. So noise in the dynamics can help you a little bit, though your rates will degrade with right. noise. It actually turns out in some follow-up work, we're able to show that you can use noise in a way that doesn't cause the rates to degrade with noise, but nevertheless uses noise to cover basically just the bare minimum of what you need. But it doesn't follow through measure theoretic arguments. Okay. So I think the thing that's kind of so you're right. Like you can go you can, for example, if there's noise in the system, you have absolutely continuous densities. You can even use log loss. But if you don't want to use measure theoretic arguments and you kind of want to understand things like purely sort of geometrically or control theoretically, you're right that the absence of noise, the absence of noise can make things more difficult. But actually, it turns out, and I won't get to in this talk, really what noise buys you, a better way to interpret what noise buys you is some sort of kind of like geometric anti-concentration rather than sort of measure or probabilistic anti-concentration. That's more of the correct.
Makes sense. Yeah.
Yeah. Cool. That's a great question.
Yeah.
Cool. So let me kind of explain, but here, so for example, Akshay is asking this in part because Adam and I and Akshay and others on the call maybe wrote a paper called Butterfly Effects of SGD, which you guys should check out, where we sort of show that like policies kind of derail themselves by going off distribution and they just don't know what to do. Here we'll show actually that it's not that the policy doesn't know what to do, it's really that the policy provably cannot figure out how to respond. And I'll explain how this works. So what we'll do here is we're going to introduce linear control systems very briefly. We'll explain what incremental stability means for linear control systems. And we'll show how there's actually a tension between imitation and stability of these systems. And then we'll gesture to how one would prove a general result. So a linear system is simply just a dynamical system where the map is a linear function. And that linearity necessitates that the map takes the following form. Xt plus 1 is axt plus but. Right? So in particular, if B is the identity matrix, then a linear system can be shown to be exponentially stable if and only if the spectral radius of A, which is denoted as the maximum magnitude of the real part of the eigenvalues of A, is strictly less than 1. Okay, so maybe one way to see this is that if you unroll the dynamics, you get powers of A, and the spectral radius of A basically dictates the behavior of the powers. So if rho A is less than 1, these powers decay exponentially quickly, but if rho A is greater than 1, the powers get exponentially larger. So what's nice is we have a very kind of easy way of characterizing stability for linear systems of this form. Cool. So we can actually prove like a nice little lemma, which says that if you can kind of compute that basically the closed loop dynamics with linear dynamics and a linear feedback policy. So a linear feedback policy is just a linear policy, and it will take the form pi of x equals k times x. And you can kind of directly compute what the closed loop dynamics are by feeding the linear policy into the dynamics map, right? And you can actually then show by computing this and using the previous observation that if B is the identity, basically the closed loop dynamics are exponentially stable if and only if the spectral radius of A plus the feedback map are less than 1. And in particular, you have exponential perturbation cystity if the spectral radius of rho of A plus the feedback map is greater than 1. Right. So this is kind of gives you a nice characterization of closed loop stability as well, just using the previous slide. Cool. So in particular, this means if you have the following situation where you have a matrix A and two feedback kind of control matrices, K star and K hat, if rho of A is less than 1, and rho of A plus K star is less than 1, but rho of A plus K hat is bigger than 1, you find yourself in the following situation. First, rho of A less than 1 means that the open loop dynamics are EISS. The situation rho A plus K star less than 1 means that the closed loop dynamics under an expert are also exponentially stable if that expert is just playing K star times X. But now if your imitator policy was trying to play K hat, then in fact, you would be exponentially sensitive to perturbations under the imitation dynamics, right? So if k hat is your imitator, then you'd be exponentially sensitive to perturbations, right? So what this suggests is basically, let's see if this is important. So kind of what this looks like is that basically you have low error sensitivity for both your open loop and your expert, but somehow when you try to learn the policy itself, you get something that just can go off the rails really easily. So to prove a lower bound, then we want to basically show that we're in a situation where something like this can occur, right? We want to show that we're in a situation where our k stars can have this kind of spectral property, but any k hat we learn is strictly greater than 1. And I'm not going to show you the exact matrices, but in fact, we can show that there's actually just 2x2 matrices, a pair of 2x2 matrices that have the following properties. So the matrices are such that the spectral radius of AI and AI plus k star I, this is like, think of this as the expert controller for this pair, are both strictly less than 1. Right, so what this is telling us is that basically that both open and closed loop were exponentially stable for kind of the linear control problem and the linear expert. But on the other hand, what we'll set this pair exists in such a way that for any matrix which could be learned from imitation learning data, I'll explain what that means in a second, there's going to be one system where the spectral radius of AI plus k hat is strictly greater than 1. Stated otherwise, there will be one system where k hat has to destabilize those systems. Right, so so both of these spectral radii both of these systems are stable, but whatever you learn from imitation learning will have to destabilize one system. Okay. So this is what we're showing. So notice that obviously there is a way to stabilize both systems. The controller k equals 0 stabilizes both systems because both systems are open loop stable. So we need to show that this applies only to k's which can possibly learn from imitation learning data. And let me explain what this looks like. Okay, so what we'll do is we'll construct our two systems, so be stable, and we'll also construct them, and this is sort of related to Akshay's noise point, to ensure that basically the span of the second canonical basis vector, the E2 vector, is an invariant subspace of the closed loop dynamics under both systems. So what this means is that if you roll out the expert policy, all the data you ever see is along the vertical axis. You don't see anything on the other axis. So in particular, it's going to require basically these systems, these two matrices agreeing on this axis so that they're indistinguishable, or rather, we'll enforce that these two systems agree on this axis so that they're indistinguishable from this data. What this means is that from my expert data alone, I cannot tell which system I'm in, and I can't identify this index I. But now what we're going to show is that if we restrict our attention to controllers which agree with the data on the vertical axis, which agree with k star on E2, these controllers, these ones that agree with the imitation data, necessarily destabilize one system, right? So there will exist one system at least where this learn k controller will have to destabilize it. Now there might be another system where this stabilizes, but at least one will be destabilizing. One way you can think of this is you can think that k star 1 will destabilize A2 and k star 2 will destabilize A1, but in fact, any controller that agrees with both of them on the vertical will be destabilizing on the horizontal. Okay. And we can show that there's an example that just happens to work that this is the case. And so you can kind of imagine using this to prove a lower bound. But unfortunately, linear systems are sort of too all or nothing to prove a lower bound. What I mean by this is that sort of if all of your data was ever on sort of the vertical axis, with linear dynamics and no noise, you can learn things perfectly. So you're never going to deviate. So really what you need is some kind of sophisticated way of embedding this into a nonlinear construction. And I'm just going to kind of hand-wavily explain how this kind of works. So essentially what we're going to do is we're going to kind of use a bump function to embed a nonlinear problem that forces the learner to make some mistake that will kind of cascade into the first horizontal direction. And then from then on, the problem will look linear. And basically, we're going to learn some sort of nonlinear, some sort of controller that will be forced to destabilize along here. What's nice about this construction is that it allows you to basically embed arbitrary supervised learning problems into the bump function, which is how we're able to get away with a result that has a lower bound for any rate to desired rate of estimation under the expert distribution. So we can kind of embed any non-parametric learning problem over here, and we get 2 to the h times the statistical complexity of that problem over here. So it shows that the result is actually kind of a whole template of lower bounds rather than a specific statistical one. One thing, okay, this kind of gives you the details of how we kind of finesse it. One thing I should mention, though, is where the simple policies come in, right? And what actually is kind of required is that a simple policy is basically one which is locally linearizable. Right? By being smooth with state-independent noise, we can actually tailor expand these policies. And that allows us to relate the behavior of this simple policy to a policy which basically behaves like a locally linear controller, which allows us to invoke this lower bound. Things are a little bit more subtle than that, and you actually have to use some work from the unstable manifold theorem. But that's kind of the intuition that you should have, is that if you're only using simple policies, you're kind of in a regime where you can only locally do as well as the best linear controller, and this is going to kind of get you stuck. So kind of maybe what's the core insight then? The core insight is actually that we see in control as a tension, a fundamental tension between being faithful to the expert, right? Having to agree with the expert along this axis, and stabilization of the unseen dynamical modes, being able to stabilize what we don't see. And somehow what this shows is that unless we're able to use sort of policies that cannot be Taylor expanded, we're not able to resolve this tension appropriately. And that's kind of the core insight from the finding. This is the RL theory seminar. I've talked a lot about stability, but I feel like it's time for me to talk a little bit about Q functions and to connect how I think of stability relating to kind of dynamic programming and other tools that you might have seen. So the Q function in deterministic control, this is review for everybody, but like at least in this audience, but let me just kind of say it, right? So in a deterministic control system, you can just write the Q function as the cost to go under the dynamics and policy, again, deterministic policy, starting at your given state and your given input. Again, I'll be quick because this is RL theory. So here's cost to go. So we all know the performance difference lemma, at least I think the audience here knows it, which basically allows you to use telescoping to represent the kind of difference between costs under an expert policy and a learn policy by looking at the differences between Q functions, where what you do is you look at the expectation of the Q function under the expert, you look at the Q functions that are induced by the learner, and you look at how these Q functions differ if you chose the action that would be prescribed by your imitator versus the action that would be prescribed by the expert. And you look at basically the difference between these Q functions and under the expert distribution, and this is an alternative way to evaluate the difference in performance. So what's quite nice, again, this is policy of the expert learner, policy of the expert. So what's quite nice about the performance difference perspective is it lets you talk about how easy imitation learning is in terms of the expert distribution by reasoning about the regularity properties of the Q function of the learner. So I'll give you an example of this. If the Q functions are Lipschitz, then you can upper bound these differences by the distance between pi hat and pi star, right? So if Q is Lipschitz as a function of u, you can upper bound these. And in particular, what this means is that the cost, imitation cost, is upper bounded by a Lipschitz constant times the cumulative norm difference between pi star and pi hat, right? So what this would suggest, therefore, is that if you have Lipschitz Q functions, you don't have compounding error. You don't need compounding error. You don't encounter this. So, and there's actually some wonderful work by Gokul Swami and his collaborators that kind of generalize this in terms of sort of integral probability metrics, where they kind of relate sort of notions of unexpert distribution imitation to properties of the Q function class. So in particular, low compounding error is guaranteed by insensitive Q functions, and large compounding error requires highly sensitive Q functions. So maybe one way to reinterpret our result is to say the following. Even if we're in situations where the dynamics are both open and closed loop stable, it is both hard to imitate the expert and to learn a Q function that is Lipschitz, and to learn a pi hat, which ensures that you get Lipschitz Q functions with your in closed loop of the dynamics. And I think this is kind of an interesting message for us as RL theorists, where we're very naturally inclined to make assumptions directly on the Q function class. So statistical complexity of the Q functions, realizability, maybe smoothness assumptions. But this actually says that if you think about systems from a dynamical point of view, you should actually think about letting assumptions on the Q functions emerge from the dynamics rather than imposing those assumptions a priori. And indeed, what your Q function class should actually look like might be something that's far less regular than you might want, but this might be absolutely unavoidable, even if the dynamics are nice, and even if your learn policy is in some reasonable class. I think I think this is something that really I didn't really fully appreciate until I started thinking about the control setting. We also have some upcoming work that we submitted to CDC that we're excited to share, where we actually show some interesting equivalences between. Oh yes, Nan has got a question which I definitely want to answer. Nan.
Yeah. So for this case, if you examine the Q functions in your lower bound constructions, are they nice and Lipschitz for the expert policy? For the expert policy,
they are, yes. So for the expert policy, they will be, because the expert policy is exponentially stable, which will mean that the Q function is going to be Lipschitz.
Yeah, so then regarding messages, I wonder if there's an opposite interpretation. That is, if you take the approach of like learning Q functions and you learn Q functions from a sort of smooth Lipschitz and nice structure, does that somehow maybe help you enforce you to slap onto the expert Q
It
function?
can't. No, it can't, because
Okay.
because the point is that our lower bound actually shows you can't even learn a stabilizing policy. And if you could learn a policy which ensured that you had a Lipschitz Q function, that would necessarily mean pi hat is stabilizing. But the point is that you cannot learn, at least when you restrict to simple policies, you cannot learn a stabilizing policy, which means that it's impossible to learn a policy that gives you a Lipschitz Q function. Stated otherwise, our lower bound is agnostic to the algorithm.
Right.
So there's really nothing you can do on the algorithmic side. In fact,
Yeah, I know that lower bound is yeah. I guess I'm like, my last question is like more general, like because that lower bound really says that you necessarily needs to change your policy class, right?
I think that, so the
But
question
I'm
is,
saying like more generally,
could you try to use the Q function to do this?
Yeah.
I think it's certainly possible that you could. I think people have tried to do this. There's some work from Stephen too from a few years ago that tried to explicitly enforce stability, which is equivalent to enforcing Lipschitz into the Q function. But it actually turns out that the better thing to do is just to make sure that you have enough, that you collect a little bit more online data, or you use a slightly better expert to collect data.
Yeah.
And working through the Q function class. Presumably, if you were in a setting where you had like really good notions of like world models, for example, if you had really good world models, you could try to enforce stability of Lipschitz of the Q function as an algorithmic tool. You could also try to just enforce stability of the dynamics. These two are kind of essentially in our follow-up paper, we're showing that these are dual to one another. So any algorithmic thing that tries to prune Q functions is basically the same thing as any algorithmic thing that tries to afford dynamic stability. It's basically like an IPM characterization of stability rather than of optimality in terms of Q functions. But yeah, I think it would be exciting to see how to do that. But from what my understanding, at least empirical attempts to do stability constraints have been quite difficult, and that suggests that maybe Lipschitz constraints in the Q class might also be difficult on their own, but maybe in conjunction with other things they might be powerful.
Cool.
Max, I have a question.
Yeah.
In this setting, the cost function is known or not known?
Known. Oh, so yeah. So in our whole construction, the cost function is known, which means that we preclude offline RL, which can even use the cost function. You can't even use the const function to beat our lower bound.
Good. And you get trajectory data from the expert, or do you get like
trajectory data? Yeah. Trajectory data. Yeah.
Okay. Then maybe I'm surprised, because somehow you could say, let me take a Lipschitz function class and try to regress onto class.
Yeah. So let me maybe say this in a different way. So what you're getting at is something called action. I think you're getting towards something called action chunking, which I'll talk about in a second. But okay. I should say that one important thing is that basically your set of instances does not come from the product class of we're getting a little bit into the weeds, but does not come from the product class of dynamics and pies, right? So the point is that like one pi star might not stabilize another f. And so we're in a regime where there's not really kind of a clear way to just sort of like ensure that there's some ground truth set where we could get Lipschitzness or stability from. So I can show you something else that will work, and that'll be kind of like the last part of the talk.
Okay.
But I agree that it's kind of hard to regress onto. The problem is that you don't know the dynamics in the construction, and so it's hard to reason about what will end up being kind of Lipschitz, because that requires knowledge of the dynamics.
And that's where like online will be really useful, because then
that's where
you
online
literally see the
exactly, or some other form of additional exploration, which is being discussed in future work. But it's sort of crucially, the lower bound leverages lack of knowledge of the dynamics. If you did know the dynamics, then there'd be a computationally inefficient algorithm, which either A, throws out all unstable policies, or B, throws out all non-Lipschitz Q function policies with non-Lipschitz Q functions. But sort of crucially, we don't know the dynamics. If we did, we would be able to do much better. Yeah.
I think, okay, like I think I'm also saying something slightly wrong. Like if you do like regression to learn a Q function and then derive a policy by like acting greedily according to that policy's Q function is not the thing you learned.
Exactly.
That policy's Q function might not be Lipschitz, even though the Q function from which you're deriving the policy is Lipschitz.
Exactly.
Okay.
Exactly.
Okay.
And yeah, exactly. And so actually, in some follow-up work, we're actually exposing like kind of the kind of equivalence between Lipschitz and incremental stability. I want to end the talk on this note, which is like how weird continuous action spaces truly are and the power of non-simple policies in continuous action spaces. And this will kind of explain some things that do work. So one is that we need new notions of coverage. So why is this? Well, we're doing imitation learning, which from a measure theoretic standpoint, from probability standpoint, we have perfect coverage. Our radon-Nikodym derivative with respect to the expert is 1. Now, we don't have all policy coverage. We have perfect expert coverage. But what we're able to show, even in this paper, is that if there's a certain notion of anti-concentration, which is less sort of measure theoretic and more geometric, which basically controls sort of a local variance of expert data. Think of this as induced by randomness over the initial state condition. We can imitate without compounding error. For the interest of time, I'm going to be super informal about this. But basically what this says is that like thinking about coverage and continuous action spaces in a more geometric or anti-concentration way is quite useful. The intuition that you should have is essentially you can learn a little bit of tube around the expert policy. I should include a graphic about this. And this allows you to learn local Taylor expansions. And by learning the local Taylor expansion, you actually get the controller right in a region, which allows you to stabilize. So we have some results of this form, and we were actually strengthening them in some future work. But it really says that for continuous action spaces, it's important to think geometrically, not just probabilistically. And also there's some work with Adam Block and I on some work in smooth online learning that also has a more geometric take that kind of has a similar takeaway. Maybe an algorithmic takeaway is also thinking about the role of, yes, Nan, 1 second, is thinking about the role of data collection as well. Yes, Nan.
Yeah, so when you say metric versus probabilistic notion of coverage, I guess probabilistic, you're talking about, things like density ratios of that kind, right?
That's correct.
And for metric, do I interpret it as something like, in a linear MDP, you can refine the coverage into something like the sample covariance matrix and that sort of thing. And in linear dynamical systems, like you obviously also have like, the linearity and.
I think it's actually quite the opposite. So in linear systems or like linear MDPs, what you get, you don't need covariant coverage, you need covariance coverage. So you actually you can get away with weaker notions of coverage that depend on like moments of the distribution.
Yeah, that's what I meant.
What we're saying is actually need something stronger. So the coverage needed in linear settings is actually weaker than sort of like density ratio coverage because it's just of a sufficient statistic. What we're saying is we need something that's actually stronger than density ratio coverage. Okay. Yeah, stronger than density ratio coverage, something that actually kind of covers the nearby metric space, even though this is off distribution of your expert.
Right.
Yeah, that's a great question. Thank you. The second thing, here's a cool little graph, is actually basically that more, we can actually show that improper policies are more powerful. So one thing that you can actually do is you can predict sequences of open loop sequences of actions. We call them action chunks. And it turns out that action chunks can kind of get around some of these problems. This is being made more clear in future work, but basically what they can do is if your expert is sort of closed loop stable, then it means that sort of the perturbation of the input to the expert to future actions is also going to be kind of exponentially like stable. And that means that if you learn a whole sequence of chunks of actions, you can kind of predict multiple steps ahead and have stability into multiple steps in the future. And it turns out you can actually feed this back into the system in a way that preserves stability. Unfortunately, I don't have time to go into this, but needless to say, there are ways around this that are purely algorithmic. And in fact, we can actually solve imitation learning in all continuous action problems that are exponentially input to stable and open and closed loop by action chunking. Here, the graph shows an experiment validating this. So we use a diffusion policy to imitate because that's very popular today. The red open loop trajectory, this is if we just like let the system go with errors, is denoted in red. And basically this is getting very little compounding error. It's basically staying very close to the system. Now we train a bunch of different sort of diffusion policies with different lengths of the action chunks. We see that using no chunking leads to a huge, very quick divergence in the policy. And as we use bigger and bigger chunks, we have more and more stability. So this is kind of a really interesting, very strange effect that I think is somewhat unique to continuous action spaces. I want to save questions to the end because there's even more weird stuff that can happen. In fact, we can actually think about instability in a very stylized way, and this will kind of be the last little bit of the talk that I want to explain. So imagine a scalar dynamical system where you have some unknown sign of the system. It's either plus or minus 1. You have a scalar parameter that's strictly bigger than 1 that dictates instability, and you have some input that you can put into the system. So this is a scalar system. It's unstable because rho is greater than 1, and you have an unknown sign. So basically it says you don't know which way the dynamics are going to push you. You don't know which way to cancel them out. So one obvious kind of fact is that if you don't know what C is, you don't know the sign, there's no linear feedback policy which will stabilize for both choices of C. right? And this is sort of because like either your sign is pointing you in one direction or it's pointing you in another direction. And so whatever your linear policy is, there'll be a sign that makes this magnitude greater than 1. Sounds super interesting. As a corollary of this, by Taylor expanding, there exists no smooth deterministic policy which also locally stabilizes your dynamics, right? Because a smooth deterministic policy can be locally stabilized. You can just argue this with the Taylor expansion, argue about linear approximation. You can even generalize this to show that there's no simple policy, one that's basically a smooth policy plus state-independent noise, which locally stabilizes. And again, this kind of follows from a similar Taylor expansion argument with a few more bells and whistles. But what's kind of weird is that there are some like really weird policies that can stabilize this even without knowledge of C. So let me give an example. This policy, which is just time varying, stabilizes the system. So what happens, right? Like the first time you try to stabilize in one direction, if you're right, good, you're at 0 and you'll stay there. If you're wrong, you'll just try the other way and that will work. Okay, this is kind of weird. There's also this other thing we call concentric stabilization. This is kind of related to more classical kind of pathological controllers in the control theory literature, where basically you can just bin dyadically your kind of intervals on both sides. And you can have a switching policy which decides which sign to use depending on which bin you're in. So if you kind of get the bin right, you've stabilized to 0. If you get the bin wrong, essentially if you choose things correctly, you end up in the next bin over and that stabilizes you back to 0. So notice this is like a highly non-smooth policy, right? Because it's going to get vanishingly less and less smooth as you go to the origin. You can smooth things out a little bit so it has a bounded second derivative, but it's still going to have a singularity here. So this is also like very, very strange. And the last thing you can have is something called, we call benevolent gambler's rune, which I think is the thing that's sort of the most shocking to me. So you can just learn a policy, which is with probably 1/2, either plays row of X or a negative row of X. So it just flips its sign. And so what this looks like is basically if you look at the probabilities that you haven't sent this to 0, at each time step with probably 1/2, you send the dynamics to 0 and you stay there, right? So each time the chance of being at 0 is growing in probability, and the chance that you're not at 0 is getting bigger and bigger. So in expectation, you're actually like destabilizing the system, but we get this benevolent gambler's rune, which is that on like a very large probability event, you've stabilized the system. And in fact, this is sort of related to a technicality in the lower bound that the audience will appreciate, which is that we decided to prove our lower bound not on L2 distance from the expert, but on costs that are bounded. So our lower bound proves against bounded costs to prevent us from cheating using benevolent gambler's rune. We can't use that in our advantage in the lower bound. But in fact, this actually shows that this is sort of that actually moving to kind of complex stochastic policies can actually give you wins if you have bounded costs, which is kind of crazy. And I think this is actually quite powerful. But by the way, we actually show that all these kind of forms of cheating the lower bound, they actually have correlates where you can beat our construction by using each one of them. You can beat it by being non-smooth. You can beat it by using benevolent gambler's rune. And I think the benevolent gambler's rune to me is kind of the most philosophically interesting. Because if we go back to kind of the purpose of improper algorithms, it really comes back to a game theoretic understanding of sort of what learning is, right? We view learning as a game between a learner and nature that picks uncertain state of the world, and we need to, through observations of that state, understand what to do. And we understand that randomization provides some power of dealing with uncertainty in games. And essentially what this benevolent gambler's rune is showing is that these kind of potentially these very powerful ways of randomizing, very sophisticated ways of randomizing, are actually necessary for playing this imitation learning game correctly against nature, right? So these kind of policies like diffusion policy, which are known to capture multiple modes in the data, traditionally they've been seen as being able to represent rich action distributions. But it's actually quite conceivable that they're doing something even smarter, that even when you're trying to imitate a deterministic expert, there's some benefit to randomization in a complex and state-dependent way that actually benefits your performance because of the uncertainty over the true state of the nature of the dynamics. I think this is something that's like kind of crazy and was kind of shocking to me after reflecting on the consequence of this. So maybe I want to end on this. There's a surprising takeaway here, which is that stochastic multimodal policies, things like a diffusion policy, they can yield benefits even for imitating deterministic policies, right? There is a benefit of improperness that resembles at least some of the capabilities of today's robot learning models. And I think this is kind of a departure point for what kind of a big theme in my research today, which is understanding what's going on with generative models in control. So for those of you that don't know, generative models have become kind of the go-to architecture for kind of continuous action control in the last 2 or 3 years. And I think we really are only scratching the surface of their full capabilities and scratching the surface of understanding why it is that they provide benefits. And this talk kind of shows that even in very simple, classical, smooth and deterministic settings, things like generative modeling, things like action chunking, some of these more complex design decisions actually have, potentially very powerful benefits. And I think there's a lot more to learn, to understand, and to harness. And I think with that, I'm happy to take questions, maybe a little bit of takeaway for the RL theorists, rethink key functions, rethink coverage, rethink policy parameterizations. And thank you.
Awesome. Thank you, Max. Any quick questions before we stop the recording?
You mentioned action chunking. What is that?
Oh, so action chunking is the practice of predicting multiple steps of the action in one go. So what you do is so your expert policy, let's say, predicts, U1 from X1, but you could also take U1, U2, U3, and U4 and predict that whole sequence from X1. And in some sense, this increases the representational demands on the policy class.
But the reduced horizon?
Well, so the naive benefit is it reduces horizon, but it actually turns out that there's a critical threshold of chunk length below which, once you can imitate at that chunk length, you actually no longer pay compounding error. And this is something it basically has to do with the fact that there will be a point at which the open loop dynamics are sufficient. Basically, what action chunking is doing is it's converting closed loop into open loop. And there will be a point at which the open loop dynamics are sufficiently stable that you kind of drown out the effects of perturbations in the policy. And if you can predict chunks of precisely this critical length or longer, you can kind of drown out some of the errors of your own learned policy.
Okay, so maybe okay, I'm trying to understand it, and here's maybe a too simplified way of thinking about it, but suppose in your problem you have deterministic starting state and you have deterministic systems, then effectively I could just memorize the action sequence of the expert and reproduce that.
So it's a little different than this. So if I just memorize the distribution of the expert, essentially the effect of this is we're reducing the horizon, right? It's just basically taking you from 2 to the h, 2 to the h over chunk length. But it actually turns out that there's another effect that's a little bit more control theoretic, which is that there's actually a critical window of action chunking, such that basically there's a policy class which includes the expert, sort of realizable policy class, where everything in that policy class is now stabilizing.
Yeah. So in that case, how does that critical window length, how is that determined? By what kind of properties?
It's determined by the row parameter of the system and determined by some other Lipschitz constants. So roughly speaking, it's going to look like log base row of some Lipschitz constants. And actually, so Nick Motney, who was on the call, and one of his students, Thomas Zhang, and Dan Frommer and I are kind of working on this as a follow-up. That's one of the things. We're also working on kind of a more thorough understanding of exactly how noising affects things. So what we can show, for example, this might be of interest, is that if you add noise and you use kind of more probabilistic or information theoretic arguments, you pay a trade-off for your noise level. But if you use kind of more control theoretic and geometric arguments, there ends up being basically this sweet spot, the sweet band of noise where you can add the noise in. And no matter, as long as you add noise sort of in that sweet spot region, you get the optimal, you get sort of the correct rates, and it's not really too sensitive to the noise, and there's no real trade-off. And essentially, one way you can think about this is you need to learning how to stabilize is basically a qualitative effect that you need to wrap around the quantitative accuracy of your policy. So really, you just need enough data that can teach you, okay, here's how you kind of make sure I'm learning a decent enough approximation to the linear controller to stabilize off trajectory. And once you've learned that, you're golden. And so we have some arguments that are based on Tassel, which is kind of work from Dan Frommer, that show that you can do this with more noise. So again, it's a very different flavor of argument than what we typically see in some of the kind of more measure theoretic takes. But yeah, cool. Open to other questions.
Maybe we should stop the recording.
Yes, I can do that.